Thank you, Hrant. Thank you also Ando, Arsen, Zaven, and all their teams for inviting me. It was very easy for me to accept the invitation because of their hospitality, and I'm always happy to come back, and also hospitality of Armenia. If you haven't tried, go to the Gum market and try some local fruits if you're a visitor, or explore the beautiful country. Yes, indeed, I was here 2 years ago, talk about Bilevel and how do we represent images, in particular, how do we get state of the art on the ImageNet. But actually, this was never our goal. Our goal is something what I'm presenting now. It was a building block what we wanted to achieve. We wanted to achieve a world model. What is the world model? It's very easy. We all have it, so it's not difficult to explain. It's something that we can, answer what if question. What happened if I, let the bottle just like that? It just falls, right? Like I don't even need to do it. In my head, I know the answer, right? I can answer this what if question. If I can answer what if question as humans, I can plan, what happens if I go around a corner, right? And so in our quest of understanding a world and making human AI useful for us, we want to first, make it understand the world and then, act in it optimally, align in our preferences. And I'll talk about how actually we built such a world model so we can act. So the agenda will be, I'll briefly introduce reinforcement learning for some of you. It might be the first time that you hear about it, describe some challenges, and then I delve into what we have done and how we actually built the world model. So we talk about exploration, interesting motivation, and I'll talk about some of our recent work. So Bilevel Explore, built on the Bilevel that I presented 2 years ago. This is our paper from NeurIPS last year, and we have a couple, 3 papers on extending the work for stochastic environment, right? Because world is not deterministic. And then we also work on some insight in what is actually being learned. We have 1 hour together, so I have a lot of slides, more than 100 slides. I don't want to use them all, but please take the time to ask me any questions, anytime, even now. Interrupt me, shout. I'll try to see questions too. All right, anytime, yes. So what is reinforcement learning? Reinforcement learning is just very simple thing. It's also something that is very natural to us, so we don't need to spend that much time exploring it, right? Like it's like defined as a learning and act in unknown stochastic environment by making some reward signal. It's maybe a mouthful, but a good example is like, let's say you want to ride a bike, but you don't even know the rules of physics, right? You want to make optimal decisions, but you don't know actually how the physics work, right? And this is one we want to do. Like the history of RL, maybe in prehistory of RL, it's more than 100 years ago in this old Tornai book, a lot of effect, but the vocabulary that we use in machine learning reinforcement actually comes from Pavlov's and his experiments on dogs, right? Like first occurrence reinforcement learning, animal learning, right? Dogs get food with the light, then the saliva comes in even if there is no food because they associated it, right? And then was a year number 1957 that actually gave a lot of rise to their 2 principles. We can go into the theory maybe in a coffee break, but one is Pontryagin principle that gave birth to what we use currently now, the policy gradient methods for reinforcement learning used every day today, and another like maybe TD learning and Bellman equation. So both of them happens in 1957 in kind of a parallel, and both of them actually still are the milestone building stones for what we are doing now. All right, so while we're not done after this more than 100 years of thinking about reinforcement learning, it's very hard. It's really, really hard, right? We need to think about the time, the long-term consequence of action, predicting the future, actively gathering experience, and dealing with uncertainty, right? We don't talk about everything today. There are many more. We try to figure out, talk about this long-term consequence of actions and dealing with uncertainty. So, but why should you care about RL in 2023, right? Maybe it's an old-fashioned field and you should just care about large language models. So, we had some advances in the last 5 years, right? Like first we had like advances with the chess and shogi and Go and games like that, right? Where we're able to get to the performance of humans. And this is what we've done with less and less, and as I was describing, less and less supervision, right? On our way from AlphaGo, AlphaZero, we could give it less and less information, right? Like at the beginning, we could just give it all the plays that history of mankind played together. Then with the self-play, we didn't need to do that, right? We could start with 0. We could just have the self-play and play 2 algorithms between each other and have algorithms figure out which one is best. And then, then we went to the museum when we can build our own dynamics, right? Where we didn't even know. Okay, keep this. Okay, I'll be like on a TV, moderating. Anybody wants to talk? Any questions, please? All right. I have 2 things to hold. So then we were able to build some dynamics, right? We didn't know the rules of the game, so let's say, like, didn't know the dynamics, and that's what we're talking about today. But we get to the point that, we may build a dynamics which is probably wrong, but it's useful for planning, right? Our world models are probably not, correct as well, right? Like, we have some notions of physics, and maybe some superstitions, and, we're not completely, accurate about the world, but we'll still be able to make decisions. That, for example, Museo also is not completely accurate what's going on, but their planning predictions are useful to make optimal decisions, right? So, it's in the goal of making optimal decisions, right? And then, things can go more difficult, right? Go or Shaggy, we should do full board. Now, we have very difficult, visual information, and we don't see even everything what's going on, right? Like in our real world, like we only see what is in front of us. We don't know what's in another country, for example, right? So 2 years ago, we were able to get to the point that they can work somehow with not having the full information, somehow, for some specific cases, building a maps of the world, right? And then, then that you can get more and more complicated, right? Like a few years ago, we were able to play the capture of flag in this kind of visually difficult environment, right? But we don't care about, like, solving the games. Even in DeepMind, we did spend 5, 6, 7 years just focusing on that. We actually don't care about games at all. That's not something that's known, or maybe it's a secret for some of you. We would like to have one algorithm that kind of solve them all, right? Solve all these 57 now even more Atari games, solve robotic tasks, and so very difficult environments that we create every year to try to get better, right? One of them that I will describe today is a set of like DM hard 8. It's very, very hard exploration task. But why you specifically want to care about RL? Even now, there'll be a lot of talks on large language models, but particularly in this year, in last iteration of training chatbots, there is a reinforcement learning step that tries to align the current outputs of chatbots for the preferences, right? And this is a typical reinforcement learning application with typical reinforcement learning algorithms that we also try to cater for the benefits what we want. There's a little peek of how this actually works practically. Oftentimes, this is one of the DeepMind model called Sparrow. Oftentimes we have some 60s, 80 transformer layers, and on top of them, we build a policy which is showing which is the next word that will be predicted, and we try to train the policy. So this is our decision-making part of the chatbots, and then we try to say to optimize some preferences. So even that RL is from 1957, it still has a lot of things to say today, and as such, is also very important things to study. And also, it's another thing that I should mention. Large language models are also a kind of world model, right? It can also, answer what-if questions. All right, so let's delve into the actual concept of RL before I'll describe like world model. Is there any questions already? So, or maybe I should ask, how many people already know everything about reinforcement learning, or something about reinforcement learning? Okay, very good, very good. Yeah. So this will be very fast then. I can focus on other things. All right, so reinforcement learning, it's a simple model of the world, where we try to learn the optimal action of the agent. So the stuff that we can control in all of this graph is just the agent. Agent can decide what actions to do or what probabilities it gives for other action. Gets to act environment, maybe changes environment, more difficult setting, and gets observational rewards. Sometimes it doesn't get any rewards, and sometimes it doesn't even get any observations. And in some sense, we have this closed loop, and the studying this kind of closed feedback loop is something that excited me all my life, right? Like how actually, how to act when you're actually choosing your data set. You're choosing what to see, right? Like if I look this way, I'm choosing my next data point. If I always work a corner, I don't even know there are people around, and maybe I will make really bad decisions on what to do. And so what we're trying to do in RL is like trying to make good decisions by learning from this experience, right? Particularly we often model with we see some observation as a probability distribution given the action that we made and the previous observation, right? We usually don't look too far in advance. We try to extract, we call this Markov property. We don't go all the way to the past. Similar for reward, can depend on previous observation, next observation and the action, or can just depend on the observation. Some things are very simple, like for example in chatbots, the observations are the text that we saw. Action is the next word in the sequence, and the reward is like how much we like that particular answer. An action we usually model as a sampling from giving what we see, what we should do, what kind of action we should take, and in 2023 or even in last, let's say, 5-10 years, we model them with a deep network, parameterize some set of weights. So in deep learning, the policies are deep nets, right? Like practically, this is our very simple frameworks that were done for environments, and that's what we're using, right? So the good example, since I was born in Slovakia, this is Armenia. Everybody knows Tetris. This is a good example of reinforcement learning algorithm. So here we can, if you have not, if you just walked in as 30 people right now, let's give it rather an example. So the state of what we're trying to do is just a current board. The action, what you can do orientation or position of the block. Reward is incremental score. You want to maximize the reward, obviously. And transition is random, it's a whole new block. And so why this is difficult? Because there's the state space, the possibilities that you could see on the screen is so big. And so that's why it's difficult to model, right? And so that's why we kind of need not to enumerate every possible action and every possible state and try to find like big tables and try to reason it in. And that's why we need to do some kind of function approximation, like learn a model, a representation of the board that will be useful for planning. All right, and so when you start to talk about rewards and model something, there's always the question that comes, where are the rewards coming from? Because when I wake up and come here and start talking, I don't get reward for every single step, right? You take a coffee, you don't get like +1, you go to sleep, this is not how we work, right? Like we have, it will be, so that's why it makes reinforcement learning very difficult, because we also, as humans, we don't get reward for every single milliseconds that we do. That things will be much faster. Sometimes we don't give a reward. Sometimes we have the reward only on long-term consequences, right? Even in chatbots, we only get rewards, sometimes after whole text that we output, right? So, ideally, the reward that we try to define, are extrinsic. Did you win this game in chess, 0-1? Very difficult, because if you never get to the point that you win any game, how can you learn? Always, when I always played with Kasparov, I always lose. How can you improve? Because whatever you do, it's bad. These are typically hard-coded reward, right? Or in difficult environment, right? Like you only get the reward where you get to some place, where you drive to some place that will solve a very difficult problem. But if you don't even have a clue where to go, you always get 0, so you cannot learn. And so oftentimes, inspired by how humans go around it, we have a lot of intrinsic reward. So Nobody gives us, cookies or beats us for every action. We have different rewards, social, like how can we influence people, how we can imitate, explain, empowerment. These are control, curiosity, a lot of our rewards, is our curiosity, right? Like, I took this walking tour in Yerevan yesterday, and they said, like, the third national sport of Armenia is gossiping. That the average Armenian gossips 3 hours a day. So, and this directly links to the curiosity. It's we're motivated to get something. And I'm talking about this one because the rest of the talk is on curiosity. And there are other losses, ring problem, explanation. Can I explain what happened? And if I can, I get reward for that. So in absence of this extrinsic reward, or if learning with extrinsic reward is very difficult, then we can supply a learning process with this intrinsic reward and try to reason with that. So this is what this talk is about, right? And why we need this kind of intrinsic reward? Because if you take this visually complex environment that you see here, and let's say you get reward when you find a golden apple or something like that, you only see, just this set of pixels, right? Like it's just imagination of what you could possibly see. And, you don't know how you should act, because you don't know, which direction this apple is, what you should explore, right? And so you cannot even explore all the world. If I tell you, look for, golden apple around here, the world is big, and if you start walking out the whole world, you cannot ever, go to every place in your life, right? So you need to carefully choose what actions you choose and what actions you completely discard, right? And so this talk is about that, like, which part of space we completely can ignore or need to ignore because we just don't have enough resources to do everything. And so with that, we'll try to see how with deep learning we can represent the world. Maybe now it's a good time to ask questions about the motivations why we do stuff like we do. Any questions? All right, don't be scared. I don't have answers, yes. All right. So how you can represent the world? So I'll give like tiny bit, like 1 minute recap what I talked about 2 years ago, just because we use this thing to build on. This was always our goal and to remind ourselves how we actually basic block to represent images. And then, then I'll go full into reinforcement learning in the setting that I provide and try to exactly solve, way of exploring and acting in this kind of visually complex environment. All right. And so one of the building blocks for that, since we don't have enough rewards or any rewards, and so it's somehow where it's a necessity because we are predicting what we already know, right? Since we don't have a lot of examples, or getting examples, labels, rewards is very costly and time-consuming. One simple thing and something that our brain does is like predicting what we already know, and trying to represent it. And there are many ways to do it. The one approach that we like particularly in our team, and we build on is based on this predictive representation, predicting something, and it's based on very simple information. Came a long time before us in the vision, that if you want to find some kind of a good representation, you use a simple intuition, right? Like you take the random transformations of an image, dog on the grass, and knowing that a view of a dog or some different transformation or augmentations or they're called differently in different papers. It's still a dog. But also important thing is not only image of a dog, but it's also still of the grass, right? So you don't want to actually find some kind of labeling. You want to kind of represent, everything. You want that your representation say like, okay, well the dog is brown, there is grass, it's looking left, and something that would be important, right? Something from what you can, not necessarily reconstruct. But let's say for each image has a vector of 2048 numbers that will be good enough to predict some kind of downstream task, right? So so we had method for this that we build on and continue building on called Bilevel, bootstrap your own latent, where you try to predict latent representation. I will not go into details because I did it 2 years ago, but I'll just mention it for 1 minute, right? So like Bilevel and other self-supervised methods, built on this idea of image of a dog is a dog, and given a transform view of an image, we look directly to some other predicted view of the same image, right? So as both views contain the same semantic information, that should be the same image, same representation, right? In this deep learning framework, we first process image with some neural network, that could be some ResNet, and then later, once we extract this visual representation, right? So here on the output we have 2048 numbers. Then we use some kind of smaller downstream networks, or maybe just a linear layer, to feed to different downstream tasks like classification, segmentation, and for this part, we use little bit of labels. But for just trying to find encoder, we try to use no labels at all, right? Right, just like recap the architecture, what we do. We process with the first view, so we do some random transformation. Here you can see we just extract the image and make it a little darker. We pass it through ResNet, and we built, one multi-layer perceptron as to predict the label, predict some vector of real numbers, so not one number. So we're not predicting this is a dog, we're just predicting some vector, some real number in a L2 space. And at the same time, we also pass another view through some copy of the network, some other iterator to predict the target, right? So we try to, from one prediction, try to predict another one, right? That's why I call it predictive representation. And what is the tool that makes the prediction is just multi-layer perceptron, right? Like we have 248 numbers, and then we try to predict the other ones, this one. And then what we're predicting from that, we try to make them closer. But important thing to notice, right? So that here we only train this part of the network. Actually, we only care at the end about this one, but we care only of this top branch. We call it online network, and we never backpropagate gradients. So the kind of targets stay the same if we don't change the weights. So at the beginning, how actually this thing works. We randomly initialize the network, so like we do random weights, which is different than doing random labels. So there is also already some biases, and then we start regressing the prediction from one view towards the fixed target representation of another view. If we do so, very interesting phenomena will happen. If we keep the target network fixed in a randomly initial network, the process already allows the encoder to run better visual representation to its random initialization. Then from there, the natural idea is to replace this random network with slightly better network that generated samples. Let's say here we could predict, network was 1% good. Then we, instead of predicting random labels, now we start to predict slightly better labels. Replace the random network generating the target with a newly trained encoder, and the result we can now generate higher quality targets, right? And we can repeat this regression training procedure by predicting these new, ever better targets. And then we keep bootstrapping this encoder representation into the targets and improving the encoder representation, and so on until we get until the perfect convergence. And then we take the encoder and claim it. This is what we do, right? So there are key ingredients that I'll just recap, because this is how we built our representation for reinforcement learning, which on the top of just images has a full dynamics. So first we need to have these image transformations, and maybe I should already say, in the reinforcement learning, image transformation is like looking into the future, because looking few steps in the future is a way of transforming the experience. Second, the target network, and the third, the predictor. So we'll see later, how this is crucial for the work. So why we like this? It's extremely simple training procedure and doesn't, require any explicit tricks to work. as opposed to contrasty method, which I described, doesn't need negative examples. So there was whole industry of negative examples mining that doesn't exist anymore, or it still exists in the fields where people still do contrastive learning. And we don't, we do stuff we don't create any pseudo labels as a clustering method, but we directly work on representation level, right? So there was a quick recap of what we did, in 3 minutes, very fast. But if there are any questions about that before I use it for reinforcement learning, and I can have more water. Yes?
I have a question about image. If it will be not rotated, for example, for 30 degrees, the input data will be very different from the original image.
Yes.
How the neural network will understand that it should be rotated back to get the same result. So it will try to rotate for all possible degrees to get this.
So we try to, this is part of creating good augmentation, right? Rotation is one of the possible augmentation, right? And to make sure that we don't just always do the specific thing, we randomize this augmentation. So we can randomize the angle which we rotate. And so to be clear, even that it looks like this is all magic and no human knowledge was given, all human knowledge, like your knowledge that you're describing, that rotation is very important, went into designing this transformation. These were not designed automatically. These were designed by smart humans like yourself, and we did a lot of hyperparameter tuning to even optimize with which probability. So for each transformation, we take 12 different transformations in the line. We apply them with a very specific probability. So with, 62% we sample crop, then apply with 13% a Gaussian blur. And these numbers, were really fine-tuned to the very digit. And it's different numbers from a top layer and second layer. And this is very important to make the best result work. So yes, so right now, we're just trusting this process to create a lot of possible diverse augmentation in a hope that this augmentation represent the task that we want to solve at the end. Because, for some tasks, rotation is irrelevant because you're just counting the colors and then you don't care about those things, right? And for some, where you see okay, is somebody looking left and right, then rotation could change it, right? So, it's very task dependent. But our approach is to generate a lot of things and make it independent to a lot of different views. But you're right, if you do some kind of almost destructive transformation, you could, produce, decrease in performance. So this view of transformation, it's kind of still omnipresent and main way of doing. And it should be said that methods are sensitive to transformation, and what was the beauty of our method, that we are less sensitive than the others, but still sensitive, so that should be said. Yeah. And yes, there's a question in the back. Yes, we do just a simple, difference, square difference. We normalize it. You can also see the cosine similarity. So you have a, one vector, 2000. Well, actually, after prediction is only 256, another 256, and you calculate the angle, and that's a similarity. It's a simple thing possible. I didn't show any graphs because I want to focus on other things, on how do we calculate, stuff in reinforcement learning. But it's a very simple thing. Or you can just say, okay, I normalize it, each of the vectors, and I calculate just a normal Euclidean distance. It's very simple. The reason is also that you want to minimize it, so you want to pass gradients. There is nothing smart there. It's just the simplest distance. Any other questions? Yes. So this method is general for any kind of possible training. We focus on ResNet because if you want to, move, the field, you need to optimize ResNet on ImageNet. Otherwise, they will not trust you that you're serious. But yes, there were people that tried this method on transformers. I have friend in Fair, Mathilde, who is doing stuff on like with kind of the person that is doing Dino, these kind of models. They've been all transformers. This method is actually network independent, and I'm actually gonna use it also for different kind of networks just now. Because for reinforcement learning, for example, for Atari games, we use different kind of convolution nets. These are not rest nets. We just use whatever works for this particular domain. Yes. So this is kind of like more of a paradigm. How to train any kind of network rather than it's just network network specific. Yes.
Is there a reason that random initialization works better than maybe a pre-trained encoder?
No, there is no reason. You could also start with potentially pre-trained encoder and improve on top of that. Yes, there is no reason. The thing is that this is the way how you get pre-trained encoder, right? So like you go for this method when you don't have anything else, or when you don't have pre-trained encoder. So there is no reason, and the output of it is one pre-trained encoder. Yes, so if you get something better and there is nothing to be improved, you can say, you can always add new augmentation and try to be robust with respect to that. Any other questions? Yes, no, yes, reinforcement learning now. So let's go to what we want to talk about today, right? Making good decisions from learning from experience, and when we want to do it here, right? Not just a simple Atari, even though it's a good test bed and we'll show some results in Atari, and not even simple, Go board where you see everything what's going on, and once you see the board, you know all the world because this is all the world. We want to, have something that will work in this visually complex environment, right? So we want to have this curiosity-driven policy. So I talk about curiosity, effective across many domains. So why curiosity? Well, I'll make a good definition later, but the intuition is very simple. One way how I can make policy do something interesting, I can just ask this what if question. What happens if I go there and turn to the right? If my world model can answer the question, okay, well, there's a bathroom, and it's correct, that's, I perfectly predict it's reward 0. But if I go that door, and I don't know, I will fall from, I don't know what's behind this exit, and this is wrong because there is actually a coffee place right there. That's a wrong prediction. So this is error of my world model that doesn't know anything or hallucinated what could be there. And this error can serve as a reward. And so I will send my neural network, my policy, my agent to the places where I cannot predict stuff. So this is curiosity role. Go to the places where you don't know what would happen. And this is how we're going to train it. We'll try to ask some what-if questions on the things that we know the answers, and then we compare our model is predicting things right, and if it's not, we reward this wrong prediction. So we'll be rewarded for making wrong predictions. I'll show a specific example. I'll just give you an intuition like where we are settling into. So in this research, we'll try to develop this universal exploration algorithm, for any possible oral agents, and we try to do it with this curiosity. All right. So I'll start with presenting, one of our results that we're presenting in last NeurIPS called Bilevel Explore. It's Bilevel, the paradigm that I presented, particularly for exploration. And it's a very simple algorithm that can be effective in many, many different domains, right? So here it's an example of this visually difficult environment, and it's an important part of reinforcement learning, the exploration itself. And it's especially important, when you have sparse reward environments, right? So when only you see this golden apple at the end. But as we scale up to larger and larger and complex environment, to the size of the real world, it becomes completely infeasible to try to explore everything in these environments, right? It becomes crucial to pick and choose which part to explore and which we'll never see, right? So all the traditional exploration method, that I've studied in the past theoretically started go to see every state once. Here it's not possible. You cannot go to see every state once. Like if you get a task, you cannot just go to the world and then to the space and explore every possible place in Mars and then you make a next step. No, like we need to make choices immediately that, well, we'll just never get to Mars. Well, hopefully, maybe some of you. So we're making this crucial pick and choose what we explore and what we just never explore. Right, so ingredients that we use for this exploration method would be this curiosity-driven exploration, right? So we learn some kind of world model, something that could predict this what-if question, what happen if. It will be neural network, no magic here. And then reward this model for fooling, so reward the agent for fooling the model, right? So the model will be latent world model, so we don't try to do something that directly predict the pixels. Oh, if I go left, show me exactly the pixels that I will see, but it will be, give me the latent representation. As in Bilevel, right? We were not predicting, full image of the dog. We were predicting representation of the dog. We were predicting the vector of 1,000 numbers. This doesn't represent the dog. Well, so this doesn't show the full image of the dog, but it represents the image of the dog. And then, yeah, so that's what I just said. And what we build on, we will bootstrap on this learning, right? We'll try to predict some representation, and then we try to get to the better and better representation. And we use this paradigm from 2 years ago that we created. We'll jointly learn the latent space and the world model. And then also, we will also learn the policy, because that's what will tell us what actions to take. Right? So in order to pick what to choose and what to explore, we take this security-driven approach, right? There is intels in 2 steps. So first step, build the world model of the world, and then we use the mistakes of the world to explore. So in other words, we go to the places with the largest world model loss, right? So, world model, just a network, what we see and what's the prediction, what is the latent impression of the world, and we'll try to, we're trying to find a policy that would go to places where the mistakes are the biggest, right? So we look at the policy, see where is the biggest mistake, so maximize the policy, to maximize over all possible potential things where we could go, and we go to the things that are biggest, right? So this world model of object that completely determines what is interesting and what to ignore. Interesting is where we're bad in prediction, and what we ignore, it's where we're good in prediction. So, then it's our world we built on this Bilevel for images and graphs and videos, and we did some other work in form. But now I want to talk about, let's say, the most challenging reinforcement learning. This is a powerful self-supervised representation learning algorithm, and extending to build this reinforcement learning setting to learn a powerful latent dynamics model that we use in the world model, right? And then we use Bilevel as an intrinsic reward. So instead of extrinsic, we use this intrinsic reward because we don't have the real reward from the world until we find a golden apple to drive this exploration toward the mistakes in the latent space, right? So this combination results in mistakes that are dynamics aware and structure, right? So we learn a latent representation that can capture more and more abstract feature, and it's robust to the noise in a pixel space, right? Because there's another thing. There will be a lot of things in a space that I should not see or care about, but I want to be robust to this, right? So in particular, right, like before we had maximized our policy for the to go the mistake. Now we kind of unpacked, we went to the details, so we maximize over the Bilevel loss. We try to find the kind of Bilevel model which has the minimal loss, that learns the dynamics, which is the best possible in predicting the world, because we still want to have a world model that makes the best possible prediction. So this is a minimization step. And on top of that is maximization, right? Because we will go to the place where the mistakes are the largest, right? So we try to find as small mistakes as possible. We improve the model. We go to the place where mistakes are higher, gather likely the better experience to further minimize the loss, improve the loss, then probably still have some mistakes. We go to the place where mistakes are higher, and so on and so on, right? So usually what happens, you know, you will try to fix the model in the place where it was mistaken. So by that, you know, it learns by natural curiosity. So this results in a single unified objective that we use for representation learning and dynamics and exploration. All right. So now we will go in a very high level overview of our algorithm. We start with the trajectory of experience. So let's say, you know, we went to, we acted in environment because at the beginning we know nothing, we have no rewards. We just go around and we observe objects or do a random action. And at the beginning, that's what we do at the beginning. We just behave randomly. And so let's see on the trajectory, we see various observations, like for example, the table and the key and the log and the apple. And some things are unimportant, as in our life, we see some things that are unimportant. And some things are important, right? But we don't know that, right? Like maybe you as humans, maybe there is something between log and the key and unlocked after. But, you know, at the beginning, you know, our AI agent doesn't know that, right? So what we will do to learn a good world model, we apply an online encoder on this world model, similarly as we did in images, to embed the current sub-trajectory. So now we're not just embedding, you know, the key. We're embedding everything what happened in the key. And here we embed everything to happen until the log, right? So it's history and dynamics aware. And then we use the target version of the same encoder to embed the future observation, right? So let's say present observation and some future observations. And then, as in Bilevel, we predict from the future, from the present observations to the future information, right? So we try to predict latent future observations. So we don't try to directly predict pixels. We try to predict this representation of the future by representation of the present, you know, so it's kind of the fortune telling. But also it's what happens if we find a key, you know, is the model can predict, well, the door lock will be unlocked once you have a key, you know, so that's kind of the idea. And we use also the same loss, you know, so this will be the loss. Well, we try to improve it, right? We try to have the best possible prediction. So we try to do this as you were asking, you know, just a simple L2 loss, equidistance between the predictions and the future observations. But we also, this will be the loss, but we also use the same loss for intrinsic reward, and then we pass it through some reinforcement learning algorithm that just optimizes reward. While since we never get any reward, so it will be, otherwise the reinforcement algorithm will be getting zeros, now it's getting something in every state, and so we can decide where to go. And here we ask him to decide where the loss is the highest, so the reward is the highest, right? All right, so I'll give an example, a specific game and architecture, so it looks less abstract. So let's talk about one of the traditional difficult problem in reinforcement learning, in exploration. It's one of the most difficult exploration game in Atari called Montezuma Challenge. You don't see it, but there is like, this is a simple, you know, when you squeeze, you know, there is a simple like Atari screen, and there is a little, you know, avatar that goes and jumps on the trees and opens the doors, and you know, it's trying to get out, trying to, you know, escape. So what we do here, it's we have several. We'll try to just describe the architecture step by step. All right. So here we have some kind of, you know, sequence of trajectory. At the beginning, we were just, you know, playing randomly. So we have just sequence of the screens. And what we do, we shared, you know, this is kind of the torso. So let's say for Atari, the best thing was some kind of convolutional nets that was used. It could be some other representation network for different things. We can try different stuff. From that, we get some kind of representation. And this is, at the end, what we're going to train. We're training this representation. But now, we want it to be dynamically aware. We want it to represent the network. So now, we create belief state. So from this representation and from past state, we use some kind of recurrent neural network. So here there are gated linear units and gated recurrent units, GRUs. And then we create a belief state, right? And so from belief state and the next representation, we get the next belief state, right? So these are embeddings of just a current stream, but these beliefs are embeddings of all possible way, right? So always we get a new screen or embedding or latent representation of a new screen with some kind of belief what was happening before, and we get a new belief, right? And then we just construct the belief. Now I didn't tell you how to train it, but the purpose of all this framework is to train those things, because at the beginning, we don't know what are the best weights. So for that, we use the open loop. So a closed loop, like we just didn't have the actions. We just embed observations. Now we have an open loop. So now we're kind of asking the question, what would happen then in this belief state that we have? We do action A. So what happens if I go and turn around the corner? So we'll try to ask model what it thinks it would happen, right? So it's the model says, we get to the next belief state. All right. It's maybe good or maybe it's completely useless. But then we say, let's evaluate how this belief state is. And then from this belief state, we'll try to predict the actual embedding of the screen, of the next screen of Atari, right? So not directly the pixels, because that will be very hard to predict every pixel right. But what we can predict some kind of latent representation. So we kind of predict something that would, this Z, that would end up here. So we try to predict this latent representation, from some neural network. And now we need to find a way if those things are good. And how to do it? We use this Bilevel, because we actually know what happened in the past, because we have the full trajectory. So we can actually try to predict the future, right? So we can look what happened in the future. We have the future embedding, which is just a copy of this embedding, and we try to make this L2 distance, so you include distance between the prediction and things right? And so the signal will come to predicting the future all the way, so this way we'll train the beliefs, the predictions of the open loop, the beliefs, the ZT, and all the way to the torso, right? So all the things end to end we'll train, just by gradient descent. No magic here, right? So similar in this BYOL, now the future observation takes the role of this augmentation. So augmenting is just peeking into the future. Future is somehow augmentation or perturbation of the past, in a sense, right? So, and then we try to minimize the loss, because we want the predictions. We want to answer the what is question in the best possible way. And so, but this is only training network, but now we want to send our agents to a place where mistakes were high. So we take this loss, and this will feed it into reinforcement learning algorithms as a reward. So we test those algorithms, and the algorithm that we use was simple policy gradient. Current one that we use in DeepMind very often is called VMPO, so that's what we use. So we tested into the Atari, but more important, we tested in a very difficult exploration environment that before nobody was able to solve. So in DeepMind, we created this DeepMind hard 8 environments, and the only way that people could solve it is with a human demonstration, to demonstrate how to work with it. So just to show how these things work. All right, so this is how it works like. Maybe it's easier. So these are the same views, different views of the same thing. It's easy to use from the top down. So the agent starts here and tries to get to the golden apple, right? So this is one of the things. The thing is that the agent doesn't see this beautiful map that can navigate. So the agent only sees this, right? It looks at the corner, it just sees weird pixels, and it needs to make the model of the world. And this is how if you're following the agent, so this is how it actually better look like. And how to get to the place that agent will just go and find an apple if at the beginning it just sees this kind of let's say almost random noisy images of what to do, how it builds the reward model. So this was our goal. And this in DeepMind, there are 8 tasks. These are 8 hard exploration 3D tasks, and Bilevel Explorer is able to get 6 of 8 tasks, so it didn't solve it completely. But other exploration methods, like for example, R&D, ICM, and stuff, they completely flatline. They don't even start learning. And so Bilevel Explorer, 100% is like the best possible performance. Bilevel Explorer is able to solve this one. It's best, but not very good on this push blocks one. There's still, this one that didn't strike a chance either. And then we try also Bilevel on these 10 hardest Atari exploration games, because that's that's what like the baseline in the field. And we were able to achieve a superhuman performance on these hard exploration games. So it's I'll go fast over that, and we get to the point where we can solve those games far. So like to summarize, the Bilevel Explorer is a simple accuracy-driven exploration method that is simultaneously does dynamics learning, representation learning, and exploration. Right? You can see the paper Talk to Me, in the coffee break. And one other thing, that I'll talk in the remaining 5 minutes is like what to do in additions of the noise. Right? This only works in deterministic environment. If you add some, for example, random pixels here, and this is easy noise, the agents could be completely fooled of what to do, and it will completely lost because it doesn't know how to represent this one. It could be even worse. We have the paper that presented in this ICML. Let's say your noise depends on your action. Like for example, it's like, let's say, the typical example in this thing is that you put the agent, it tries to represent by curiosity. And so let's say I have a TV here, which has a noise, and agent will try to predict what's the noise in the next time. So, well, it cannot predict it, so the agents, what they do, they go in front of the TV and watch the noise because it's very interesting. It's very interesting for them. There are a lot of rewards and unpredictable. And so they completely break. And it's even worse that the noise, when it depends on action. So imagine you have a really bad TV and have different channels. Each of them have a different noise. Really interesting, for the agent. Every action, so it's action-dependent noise. And so in Atari, they did it like you press jump, and instead of doing jump, you just repeat the previous action. So it's like create additional noise. The humans, totally fine. They don't even notice, that they're just like they just, and it works well. But for this kind of representation learning methods for RL, they completely, they completely flatline. So we would like to, this is what you see before Bilevel Explorer, but when we get, with these sticky actions, it completely goes down. And the R&D completely breaks. We would like to have something that even in the presence of noise, and we have called this method Bilevel in hindsight, and we present in this ICML. I'll mention in a few seconds, is able to deal with kind of noise. Because there are different kinds of noise. Noise can depend on environment, on the actions, on both of them, and so on, right? So different methods in the past can depend on the different kinds of noise, but there was no method until now that's able to deal with all different kinds of noise and is dynamic somewhere. So I'll just present intuition because I don't have enough time. And for everything else, please just talk to me. So the intuition is, well, let's start. Consider you bet on the coin, right? You toss a coin, but the coin is hidden from us. I don't tell you if it's bet on, if how it landed. And we take the action. You can bet on heads and observe the outcome. I lost the bet. And 2 facts are clear, right? A priori, we could not even predict this, no matter what. And a posteriori, so after this experiment, we'd use the latent fact that coin must have landed tails because we lost the bet. So we could not win it. So because we know how the game works, like if it's tails, we lost the bet. So to be extra clear, if we know how the game works, then in hindsight, the outcome is obvious. On the other hand, if we don't know how the game works, then we would not be able to infer Z, nor we would know how to identify the outcome. So this suggests that instead of curiosity, we can measure our understanding of int transition based on how much outcome makes sense in hindsight, so after the experience happened, right? So instead of asking, as we were asking in the last 15 minutes, that understanding is to predict the outcome a priori, so predict this future outcome, using Bilevel. Now we're going to ask how to reconstruct the outcome a posteriori. So in example, with the TV, every TV noise, I additionally try to inject something like the TV noise, so it will be easy to represent. I have 1 minute, and I know people are very strict here. I'll finish on time. So I will skip, the technical part, how we achieve this with neural networks. So we built some kind of model for that. I'll just mention that this has a kind of drop-in modification to Bilevel Explore that is able to do this prediction and reconstruction a posteriori. It doesn't add almost any additional, training steps, and is able to deal with these stochastic transitions here, right? So here we have we created these weird noises where we have a Brownian oscillation, random pixel noise, on-demand noise, like switching the channel, and we were tested if our methods are robust to that. So I'll just quickly, we have some theory, no time for that. So we have some kind of explanation. I'm happy to talk about it, why it works, and what actually we're learning. This is another paper we had in ICML. And short story is that we kind of learned, Bilevel learns kind of the matrix. So every policy you can represent also matrix as okay, from which state you go to which state you end up to, or matrix, which latent step you are to which latent step you end up to. This is kind of determined by the policy you're taking. And we showed that by learning Bilevel, we're kind of learning something that corresponds to the PCA, the traditional PCA of this particular matrix. So we're kind of learning something that makes sense, and we compress this information into some small number of eigenvectors. So talk to me more about this on the break, and I'll just finish with the references, including the most current one. So thank you very much.
I have one question. Does your model have any memory concepts? I mean,
no. No, not right now. We were thinking about that into scaling to the bigger stuff. Like in parallel with this work, we try to also design very difficult environments. Like, for example, have many different blocks, and you need to have the switches in a particular order. And so, where memory could be useful, we were thinking also of adding memory, but at the end, we'll focus on something clean that we can just see how it actually learns the exact things. But yes, it makes sense that memory could be useful, either using, we're also experimenting with transformers or with some kind of explicit memory that can sometimes do better in.
Yeah.
So, but right now, no.
It can solve, for example, problem of fluctuation of when agent doesn't know what to do. So, for example, if you see the same environment, it can. I'm not expert of RL, but I think that maybe it can do more deterministic actions. This is the first question, and the second question: how long future it can predict? I mean, imagine the environment, some cycled environment, and the goal is to go to escape from this environment. And if he can in some way predict that this is the cycled environment, maybe the best solution is to stay and not do any actions.
It could be, yes. So it's a good question. What more practical question we ask, like how far in the future it's actually useful to predict, because it can predict, we can ask it to predict any possible steps in the future. It's just a prediction problem. Usually, to the predicting something far in the future may be less useful because there is less signal from it, because it's not. So what we found empirically, predicting 7-8 step is something that worked the best as. Beyond that, we didn't get much improvement over the 7 to 8 steps. But so usually that's what we do. We're predicting, but also predicting 1 step, 2 step, 3 steps, up to 7 to 8 steps.
Thank you very much.